Mats, thanks for the kind introduction. So it's always funny, you know, whenever somebody mentions concurrent constraint programming, sorry, Vijay, I have to say that, then you know, my instant urge to reply is, you know, I was young and I needed the money, right? So but let's get over with that. So what I'm going to talk about today is a project that somehow is a collaboration between SICS, KDH, and Ericsson, right? And basically what we're doing, we're actually generating code, you know, executable code to be executed on real hardware. And not very surprising for today's theme, we are using constraint programming for doing so. So I will give an introduction into the project, and Roberto then will give a short demo that will somehow reinforce the points I'm trying to make. Right, so Unison, the name of the project, is part of a compiler, right? So a compiler actually turns programming source code, typically written by a human, into the same program, you know, with the same meaning in assembly code to be executed on a machine. And what typically happens inside a compiler is you have a front end that basically analyzes your input program, checks for errors, and generates a program into some intermediate representation. Think of, you know, the most basic, simple assembly language with any commitment to any particular architecture detail you can possibly think of. Then you have a mid-end or optimizer where you perform all the platform-independent optimizations on your program. And then you hand it over to a back-end or a code generator where you generate a program, you know, in a specific assembly language for a specific processor architecture, right? And what Unison actually is concerned with is actually the code generation aspect, you know, of a compiler. So the backend, right? So how do you do that, code generation, right? It's typically, there are three different tasks you have to take care of in code generation. One is you actually have to find or select instructions from the real hardware architecture that implement, you know, the operations from your intermediate representation. And you can see this as a clear aspect of optimization. The fewer instructions, the better. You know, the less clock cycles the instructions need, the better, and so on and so forth. The other thing you have to do, you have to schedule the instructions. Basically, you want to reorder the instructions in order to increase the throughput, right? Exploiting many of the advanced features that you have in a modern, you know, CPU. And the last, but definitely not the least thing that you have to do is you have to allocate registers, right? So as much as you can possibly pull it off, you try to squeeze program variables, or temporaries, as I'm going to call them, into registers, because, you know, access to registers is so much more faster than access to memory these days, right? And the way how you typically organize it in today's compilers is that you take these three different tasks in a certain fixed order, right? So, for example, you first select instructions, and then you schedule them, and then you decide on how you assign or allocate registers. And there is a fundamental problem to that, because the decisions actually interdepend on each other, right? So whatever you do for instructions scheduling might actually, you know, have a very deep, you know, interdependency with register allocation, vice versa, and so on and so forth. The other way that you typically can make the observation is, you know, compilers is one of the oldest topics in computer science. Right, so it has been around for a very long time, and so at that time it was believed, you know, these are optimization problems. We cannot do anything but heuristic algorithms. And if you think that heuristic algorithms are simple, you are wrong. Right? They are super complicated, ugly as hell. Complicated, really, right? And then, you know, it is not being helped by the fact that, you know, we cannot increase clock speed any further. So, but we still have transistors to spare. So what do? We make the CPUs as targets uglier and uglier. More complicated, more complicated. I'm pretty sure that there is a conspiracy of hardware designers to make the life of compiler writers miserable, right? That's what they are doing, these guys, right? And if you look, for example, to Intel's x86, you know that pretty much everybody, I think, of us has used it. You know, you just look to the last 10 years. It is MMX, SSE, SSE2, SSE3, 3.1, 3.2, 4, 4.1, 4.2, AVX, 128, 50, 256, whatever. You know, not easy to program, right? All right, and so this comes with disadvantages. If you do not reflect the interdependencies, you pass, you know, the opportunity to generate optimal code, right? That's it. Also, if you have these complex heuristics, you get something that is inflexible, error-prone, right? And then it's also very difficult to keep up with the evolution of processors. And trust me, they evolve rather quickly. So each time you buy a new mobile phone, you know, the manufacturer of this mobile phone will have added some new instructions in the instruction set, right? Just because you have these additional transistors for free. Just, you know, burn them on something. Right. Okay, so what we want to do in Unison, or what we are doing, is actually something different. So we still start with a program in intermediate representation, but rather than generating code, we generate a very high-level model, right? And the model is based on the input, of course, the input program, and a specification of the processor that we're going to use, right? So basically, think of the specification as what are the instructions that are available, what are the properties of these instructions, you know, number of clock cycles, what kind of functional units are being used, and so on and so forth. And then actually right, on my computer, this actually works. The constraint model, right? So the three boxes are instruction selection, instruction scheduling, and register allocation. Here, there, whatever. And so the key point is that the interdependencies between these three different sets of decisions are perfectly reflected in a single constraint model, right? And actually, generating a model is much, much easier because it's so much more high level than generating the actual code, right? So I'm pretty flexible. And then what we do, we take this constraint model, hand it over to an off-the-shelf constraint solver. Forget about the comment that Mats made that I actually have a history in building constraint solvers. You know, it is really off the shelf, right? So I'm a split personality. Here I'm not thinking about tinkering with a solver, I just use what's available. And then, you know, solving this model will actually generate the assembly code for us, right? So the solution to our model is the actual assembly code that we want to execute. So the advantages are pretty obvious, right? It is possible to generate optimal code because all the interdependencies are properly reflected. Just changing the processor specification gives you actually a complete code generator, right? So you only have to write a high-level specification of your hardware architecture, give or take. It's an idea. There is always a little bit of tinkering involved, right? But more or less, yes. And you know, given that this is not as complicated as generating code, the likelihood that you get actually correct code is pretty high, right? All right, and what we already used, so as I said, you know, we use a high-level model of the problem, and we already went through what a constraint model is in principle, right? You have variables, you have constraints that define which combinations of variables, values the variables can take on, and then the solution of a model that we compute satisfies all constraints. Typically, we also optimize for certain criteria. And the good news is that this area has made tremendous progress, right? I mean, there is of course, progress just by the more powerful hardware that powers these solvers, but also from the technology that evolved from, you know, something of a first idea into something that is pretty mature. Right, and of course, you know, it's not as simple as Peter tried to tell you this morning. So, because, you know, the point is, you not only have to model in order to capture the problem, but actually you also have to model in order to be able to solve the problem. and that can be quite hard. Right, so when I say optimal, does not mean the very best code. It means optimal with respect to the model of these three different tasks. Right, so it matters how sophisticated your model actually is. More sophisticated model means better code, right? And here, I'm only focusing on the a combined model for register allocation and instruction scheduling, which is basically Roberto's baby. And I have another grad student which focuses on instruction selection. And in the end, of course, we are going to combine them. And we are particularly proud, we are very proud of both models that we have because both are unique in the expressiveness they offer. And if you see why, then you see it has a lot of features, in particular for register allocation, that are unique to the Unison approach, right? I will not go into the detail, and I will just give you an idea of the technical thing. So basically, our unit of compilation is a function. That is the input to Unison. Then we have it as a control flow graph consisting out of basic blocks, where you have the intermediate, where we already have done instruction selection. And we build on top a standard compiler toolchain called LLVM. And we assume, which is also state of the art, and LLVM does that the basic blocks are in SSA form, static single assignment. And the only trick is you assign a temporary or program variable at most once, right? And so that means if you assign it only at most once, the assignment is unique to a particular basic block, right? Then we do instruction scheduling, where we have a model that is local to one particular basic block. Don't try to decipher the dependency diagram. It doesn't mean very much. It is a real example, but I'm not going to do that. This is a classical scheduling problem where constraint programming is really good at. And you have precedences, being derived from the dependencies among data dependencies and control dependencies between instructions. And you have resource constraints where resources are, for example, that you cannot possibly, a server instruction cannot exceed the capacity of the functional units, the data units, the memory units, and so on and so forth. In particular, if you have a very long instruction word architecture, and also the bundle width of the processor. Right. Okay, so let's go over that. Then the way how we do register allocation is actually we have a local model for each of the basic blocks. And there, for example, the type of variables that you would see in the model are, for example, for each instruction, you would have the issue cycle, so the clock cycle when the instruction is being issued. Then for the temporaries, you would actually have a mapping that tells you in which register the temporary will be allocated, possibly including memory, and so on and so forth. And the type of constraints, for example, that the life range of temporaries that have been assigned to the same register do not overlap, right? So that they do not overwrite each other's values, right? And where the life range of a temporary is basically ranges from the cycle of the definition of the temporary to the cycle of the very last use, right? So you see that there's the definition, and there's the last use, and that defines the life range. And these life range are not allowed to overlap, right, for temporaries that end up in the same register. Then what we do, we actually have a global model that combines the local models for each of the basic blocks. And the way how we do that, so the decomposition is actually also useful for the solving process. And what we try to do, we try to assign temporaries as much as possible to the same register using a process called coalescing that correspond to the very same variable in the original program, right? So this is the whole idea. There are different temporaries in different basic blocks, but in the end of the day, we try to squeeze them into the very same register to avoid moves across block boundaries. Right. Okay, very good. This is the basic idea. If you compare it to LLVM, then you will see that actually, this is for digital signal processor architecture, Qualcomm's Hexagon. And the benchmarks are 2 years old, so that might mean that both the LLVM backend for Hexagon might have made progress, but also we have made progress in that time. And at that time, if you compare a standard benchmark set, MediaBench, then you have Unison will offer a 7% mean speed up, right? All right, so one thing that is important, I think we had this discussion already earlier. It is infeasible to always compute the optimal solution because time might not be, but these methods have a very nice anytime behavior. The more time you invest, the better the quality of the generated code, right? All right, it scales reasonably well, but we still have to work on that. If you want to know more, so we actually, just a month ago, released Unison as open source, so it's on GitHub. And now, Roberto will give you a nice demo.
Thanks.
I need to spend exactly 20 minutes.
Is the mic on? Yes. Okay, great. Right. So I apologize because the slide is not displayed fully, but hopefully you can see most of the content here. So this is the same function that Christian used during the presentation. The factorial function written in C code is the imperative version. And in this demo, I'm going to show how we can generate code for Hexagon. As Christian mentioned, Hexagon is a signal processor that is present in this Snapdragon system on chip, which many of you might have actually if you're using Android mobiles. So this function has 3 main basic blocks. In the initialization basic block, the variable f is set to 1. Then we have this while, where f is multiplied by n, and then n is decremented. And then finally we return f. So very simple function. Right. So let's look at the input to a Unison. So here we assume that instruction selection has already been performed. So we use LLVM for that. So this is the input that we will get if we want to do register allocation and instruction scheduling simultaneously. So there is nothing really special about this format. It's pretty much a standard representation that LLVM is using, a control flow graph with 3 basic blocks. You can see in the top the initialization, in the middle you have the loop, and then the last block, and then you see it's in a static single assignment form, which means no temporary is defined twice. Right. So this is a very small function, right? So one thing we could try to start with will be just enumerate all possible decisions that we can take regarding register allocation and instruction scheduling together. Just pick the best one and go with it. There we will get the best possible code. And since factorial is a very small function, we will hope that we could do this efficiently. Right? So this is what I would call the naive approach, a brute force search approach. Right. So in this animation, what I show is the search tree. There is a tree that is formed where the solver is trying all possible combinations of decisions, right? And just looking for the best one in a naive manner. Just trying to enumerate all possible register allocation decisions, like assign this temporary to this register, to this order, to this order, I schedule this instruction here, 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 all possible combinations. And you see factorial is a tiny function, but this doesn't work, not even for factorial. So you see how many decisions are there to deal with. So we need something more advanced, a bit more advanced than that. What I call constraint solving. Basically, we apply constraint propagation techniques, as Arnaud discussed already in the morning. And if we do that, then it's obviously quite trivial to get the optimal solution. So the orange diamond you see on the top will correspond to the optimal solution. That means the best possible code that we can get for factorial for Hexagon processor according to the model that we have. So we can take a closer look to this. For example, let's look at the scheduling that we got in the initialization block. So here in the vertical dimension, we have time, and then we have the different instructions of the hexagon processor. And we see that the 3 instructions, you don't need to understand what they exactly are, but the 3 instructions that are used in that block are scheduled in parallel. The solver decided to schedule them in parallel. Then in the main loop, we are having 2 cycles. So in the first cycle, we have an addition, which is actually the decrement of the induction variable. Then we have a multiplication and a comparison. And in the next cycle, we have a jump. And then in the return block, we have a move, a register to register move instruction. And I will come to that, back to that in a while, and a jump and return instruction. Other aspect that we can look at, so that was the schedule that the solver came up with. Right? We can also look at the register allocation that the solver decided. It will look like this. Here we have the 3 main blocks. Can you see them? Maybe like this. Right, so each rectangle here corresponds to a temporary. And in the vertical dimension, we have time again. And in the horizontal dimension, we have the different registers of the hexagon processor. So register 0, register 1. This is a minimized version of the hexagon just for demonstration purposes. So here you see very few registers, but in reality, you will have something like 32 of these columns or so. And then each temporary is represented by a rectangle. And then the rectangle is placed in the register to which the temporary is allocated. And it spans for as long as the life range of the temporary. Finally, we can look at how the data flows among instructions of the processor. Again, here we have the initialization block. We can see, for example, that the value generated by the comparison flows to the jump, conditional jump instruction. In the main loop, we can see we have a multiplication here, the addition, the comparison, and the jump. And interestingly, again, in the return block, we have a jump and return instruction, but we also have a register to register move. So in the very best solution the solver could find, there is actually one additional instruction that wasn't there in the input that we got, but that the solver decided to add. So this is the best function. Still, we have one additional register to register move. And I will show you why. Remember that the goal of register allocation is getting rid of as many of these register to register moves and copies and spills as possible. All right, but first let's compare the code that we generated with Unison with that state-of-the-art heuristic compiler will provide. So to the left, we have the code generated by Unison. To the right, we have the code generated by LLVM. How many of you are used to reading assembly code? Okay, that's good. So, but you don't need to understand much here, just that this first row corresponds to the initialization block that is executed in, right. As I discussed before, so in Hexagon you can execute multiple instructions in the same cycle. Right? It's a very long instruction word processor. So here, for example, we have a comparison together with a conditional jump instruction and the initialization instruction. Then we have here the main loop, which takes 2 cycles, and then the return block that takes 1 cycle. And that's for Unison. What happens with LLVM? Well, in the initialization block, LLVM requires actually 2 cycles rather than 1. So even for this tiny example, Unison generates code that is slightly better than the one generated by LLVM, which was actually surprising for me when I first tried out this little example. I didn't expect any difference because this is really the easiest function you can think of. So let's try to understand why this is the case, actually. So this is, again, the factorial code. And the key factor here to recognize is that factorial has 2 variables, basically, the n variable and the f variable. and both of them are live at the same time, so you need to keep the values of both of them stored somewhere during the execution of factorial in different places. And the calling convention of hexagon forces both of them to be on the same register, register 0. So n needs to be on register 0 at the entry of the function when the function is called. F needs to be in register 0 at the return point of the function. So we have kind of a conflict here, right? We try to assign two variables to the same register, but they need to be alive at the same time. So what the register allocator needs to do in this case is to temporarily move one of the variables to another register at some point so that they don't clash, they don't override the value of each other. And that's actually why we have this register-to-register move instruction. So in the solution that Unison generates, Unison decides to keep n in register 0 during the entire execution of the function. And then to have f on register 1 since it's initialized. And just in the very last cycle, f is moved to register 0 just before return to satisfy the calling convention requirements of hexagon. LLVM kind of tries the opposite approach. So it moves n from register 0 to register 1 almost right away. And then it keeps n in register 1 until the end, except here for this. This is kind of an spurious register-to-register move. I don't understand why LLVM is doing that. But it's not affecting performance. And then f is maintained in register 0. I'm sorry, you cannot see that in this slide. But basically, Unison and LLVM are taking quite the opposite approaches, right? So Unison is preserving n in register 0, and LLVM is preserving f in register 0. These two decisions might look kind of symmetric, but there is actually a difference. And this difference you can only recognize if you reason about instruction scheduling at the same time as you do register allocation. So Unison understands, by considering also the instruction scheduling problem, that moving register f from register 1 to register 0 at this point comes for free, because you can schedule that in parallel with the jump and return instruction. In the case of LLVM, it tries to do the move right away during the register allocation phase, and only later on, during the instruction scheduling phase, which doesn't look back, it realizes that that adds a new cycle. But then it's too late. There is nothing you can do. You cannot come back. You cannot try different approaches, right? So the two decisions from a register allocation point of view seem to be same, I mean, as good. You don't know what to take. You might as well take the one LLVM took. Only if you consider instruction scheduling at the same time, you realize that one is better than the other. And that's the key why Unison can generate better code in this case. All right, so if you just look quickly back to the example, we see in Unison, we have this register-to-register move here in parallel with the jump and return instruction. In the case of LLVM, we have the register-to-register move here at the beginning. And adding this at the beginning increases the critical path of the initialization basic block, so it adds a new cycle to it. So this takes 2 cycles rather than 1 here. So that's the difference. It's a tiny difference because the main loop takes the same amount of time, but still, factorial is a trivial function and you wouldn't expect a difference. Okay, that's for factorial. Now, what about real-life code? So we claim that Unison can generate good or near optimal, sometimes optimal code for at least medium-sized functions, and this is an example of such a function. Decoding algorithm from the GSM protocol. Don't ask me really what it does. I don't. But if you look at the input that we get, well, it's kind of a real-life function, a complex control flow, 100 or 200 instructions, and so on. So here I'm going to illustrate another capability of Unison that Christian already mentioned, and it's that we can generate code iteratively, so progressively. The more time you give to Unison, the better code you can expect to get. And you can abort the process at any time and get something. Actually, what we do in practice is that we run LLVM, get the code generated by the heuristics, and then tell the solver, now go find something better than this. So we use already the code that a good compiler is giving us as a starting point to just optimize further. Right. So here we are doing a bit of pre-solving, and we have talked already about pre-solving a bit this morning twice. And then we start this iterative process. So we enter first iteration, we don't find anything. Second iteration, we find one solution. Then there is a bunch of iterations where we don't find anything, you see. And then in the last iteration, we find a better solution. So in every iteration, we might not find anything, or we might find a better solution. If we find something, it's going to be better than what we have already found. And here I cut the process after 10 iterations. We could still be waiting, possibly, if I didn't cut the process. Right, so the solver in this case found a better solution than the one from LVM, but not the optimal, or at least it couldn't prove that the solution it found was the very best one. It might be the best one, but the solver couldn't tell us. What we can know from the information that is provided to the solver is that it's expected to improve the quality of the code generated by LLVM for this function by 7%. So it's a fair speed up. And equally interesting, the solver is telling us that in the worst case, we are not farther away than around 3% from the very best solution found. It could be so that we are as good, that this is the optimal solution, we don't know. But in the worst case, we are not farther away than 3%. And just to finish the demo, we can look again at the code generated by Unison and by LLVM. So again, to the left, we have the code generated by Unison. To the right, the code generated by LLVM. And there is no way to understand really what's going on here. Yes. But you can identify blocks where we cut 1 or 2 cycles here and there. So for example, in the first block, we have 4 cycles for Unison. And then we have, we have 6 cycles for Unison, 7 cycles for LLVM. And if we scroll down to the function, here we have another block where, and this is actually the body of a loop, where Unison manages to pack everything into 3 cycles, while LLVM takes 4. So I hope I convinced you that Unison is not just useful for solving tiny, useless functions, but also real life stuff. Thanks.
Who has the mic?
How are you getting your lower bounds on optimality?
Sorry, the question is?
How are you getting lower bounds on optimality?
Oh, just by propagation, and by propagation, and also by relaxations.
Right.
Okay. So
but rather naive relaxations.
Okay.
Hmm?
Two related questions, not quite on the main topic, but associated with it. The first is obviously, if it is the case that developing a constraint-based model for a processor is simple, then you could help the people designing processors navigate that space much more quickly. And the second related question is, in fact, does it become feasible to do some kind of an automated search within processor design with the goal of generating, high quality code for some target codes?
I think you can.
Right. I mean, this is really the ultimate prize, right? I mean, and that you really want the hardware design organization to be able to explore the design space, right? So I mean, that they can actually try out that, is it worth to increase the instruction bundle size, or is it better to, add a new register bank? And you would still have to, manually manipulate, or at least you would have, a certain number of processor specifications or variations of processor specifications, but then you could automatize it to a certain extent. Right? And so this idea of design space exploration is actually pretty old, right? So and people have been writing books about it actually. And then there is always, so the first book I read was I think published 5 years ago, and then I was really excited and I read it, and then it says, oh yeah, and then with a little bit of manual intervention, you get actually a new backend for the compiler so that you can try it out. So basically, people know this, but it has never been done for real, really. And yeah, but this is definitely, what is the big price here to go for.
So I have an observation, which is our new processor that we have now is the gap between the memory and the processor is extremely huge. Some projects at Stanford really do these inter-functional call optimizations. So they don't use memory in the middle. And actually they get like 5-6 times speed ups of the code. For example, a machine learning library or something like that. Right. So something like that could be done with Unison. I think that would be great. Because
David Bowman made this argument before. So one thing which is, if you think about, the models, when we think about processors here, this is actually, forget about general purpose processors. That's the past. That's not the future. The future is a complete mess, right? So it will be accelerators. Everything will be completely heterogeneous. And yes, this is a direction in which we will be going, right? Programmable accelerators, multi-core, very heterogeneous, and so that's where we're moving. And the argument is typically something like this. Yeah, it will be difficult, but with this technology, it is most likely to be easiest to do that, right? Than with something that is not as flexible and not as easy to modify.
It might be interesting to look at because the gain is
absolutely
huge.
The
gain is huge. It's not
we're going to submit 2 grant proposals tomorrow that go in that direction.
So if I understand what's happening here, I think you are getting a better code because you pay more attention to instruction scheduling in this particular case. And it's good that you do, but this is a processor that has a lot of registers. Have you done something similar for a memory poor, for a register poor architecture like x86? Do you have similar numbers or some numbers for x86 that?
An observation about this processor is you might think 32 registers are a lot, but it's a very long instruction word processor, which means that many instructions are executed in parallel. Many more temporaries are live simultaneously. So as a rule of thumb, maybe you should divide the register file by a size of 4, as you can execute up to 4 instructions per bundle and so on. So I would argue it sometimes, or often actually, we run out of registers even here. But no, we haven't tried for x86 yet, and we'd like to do that at some point. The problem there is that we don't really have a good model about how things are going to execute in practice. So whatever we optimize for, it might not be a very accurate model of what we end up with. That's kind of a really open question for us.
I mean, we know that basically we're using the cycle estimator from LLVM, right, to tell us, what to expect. We know for one architecture that the cycle estimate is pretty accurate with respect to the real clock cycle number when you're executing on a simulator. There's for x86 we don't know, right? The surprising thing for us was a different thing, is actually when we tried MIPS. MIPS is really the worst case for Unison, because it's so super regular, you would expect, that Unison should not generate any better code than LLVM. But even for MIPS, it generates better code. And it's really not that you take the instruction scheduling serious, but that you really reflect the interaction between instruction scheduling and register allocation, right? There was one more. All right, okay.
Can I add a technical detail? Since I'm
I mean, you're the master. I mean, we are at your command.
Oh no! But come on! But I'm in the party. All right. So we talked about minisync earlier today, and as Roberto explained, his solver uses Gecode, and it uses very clever, very let's say tailor-made search procedure for this. We also have a complete minisync model for this thing, and we use this for different purposes. Mainly, maybe I could describe it as quality assurance, and also as a way to sort of pit the two solvers against each other sometimes.
Sometimes we find they have complementary strengths as well.
Yeah, yeah. Well, on that note, let's thank the speakers again.